Welcome back. This video is going to cover Holt-Winters time series model. So this is really the third video in a sequence on exponentially weighted moving averages. And you really need to watch those previous two videos and understand them if you haven't already done so. So the first video covered what's called simple exponential smoothing, and that method is used if you don't have a trend or seasonal effects. The previous video covered Holt's method. So Holt's method builds on simple exponential smoothing by allowing to have trends, but not seasonal effects yet. Holt-Winters extends Holt's method further by allowing seasonal effects. So whenever you've got a data set where there's probably some seasonal effects going on, that's a signal that you're going to need this Holt-Winters method. The way to think about this is sometimes it's called triple exponential smoothing, because we're really smoothing three things. We're going to be smoothing the level, then the slope, so how is that level changing over time, and then also smoothing seasonal effects, where maybe our sales are higher in the fourth quarter than the third quarter. And that would be an example of a seasonal effect that happens every year. One of the key benefits of smoothing all three of these things is that the level effects, the trend effects, and the seasonal effects can all evolve over time. They're not going to be constant over time. To really understand what I mean by this, let's take a very simple example. We're going to go back to regression models for time series. And let's just say that I have a regression model that looks something like this. So yt is equal to some intercept plus a slope times t. So what I have so far is a model that looks something like this. Here is my intercept, and then over time, maybe my slope is increasing. So for a run of 1, as I increase my time period from 0 to 1, the y value, I forgot to label my axis here, increases by beta 1. But I'm going to add some seasonal effects. So let's say beta 2, we have beta 2 times S2 plus beta 3 times S3 plus beta 4 times S4. Where S2 is equal to a dummy variable that takes the value 1 if the current quarter, so if T is second quarter, so quarter 2, 0 otherwise. So every time it's quarter 2, we're going to add an effect beta 2, otherwise we don't add beta 2. S3 is going to be a dummy as well. So if the current time period is in quarter 3, now we could go write this mathematically, but that's probably more confusing than needs to be. We get to add then beta 3, otherwise we do nothing. And then S4 is going to be the season 4 dummy. So if T is in Q4, then S4 is equal to 1, and we would then add beta 4. Basically what the data would look like, let's just maybe give us some concrete values here. Let's say beta 2 is a half, beta 3 is 0, and beta 4 is minus a half. Then what would happen is periods 1 and 3 are going to be on the line, whereas period 2 is a half a unit above the line. Then, okay, here's period 2. Period 2, we're back on the line. Period 3, we're a half unit below the line. So this is period 1, 2. This would be period 3. Then period 4, we're back on the line. Period 5, we're above the line. Period 6, we're back on the line. And then period 7, we're below the line. All right, so what I want you to notice about this is the betas don't get to change as time increases. So they are, it doesn't matter what year this is. It could be 100 years in the future, or it could be now. If it's second quarter, we add a half, and that's set in stone. Likewise, the trend doesn't get to evolve. It's always whatever I made my trend is here, beta 1. That doesn't get to evolve over time either. So what we're going to do with exponential, with Holt-Winters method, is allow for this slope as well as the seasonal effect to change over time. So the classic example of this could be something like electricity demand. So before air conditioning hit, there was less seasonal variation in electricity demand. After electricity came in, then the demand spiked whenever we had summer with a lot of heat, therefore a lot of demand for electricity from air conditioners. Okay, so Holt-Winters would allow us to capture that, but then the trend could also change as well as the level function. All right, well, let's begin with the additive model. So there's actually several versions of Holt-Winters. So the Holt-Winters additive model looks a lot like the regression equation that I just scribbled out. But let's go back to my scratch pad here. And so this is t, this is y. And so let's just say my data looks something like this. All right, and so maybe I've estimated some line, and now I want to forecast into the future. So I could just put a giant question mark. What's going to happen out here? Because this is time period big T. Well, the answer to that question, what's going to happen out here, is we're going to do a linear extrapolation with a seasonal adjustment. So perhaps this is my L big T value, and if I want to go H periods into the future, I'm going to take whatever the current slope is. So this is my current slope, call this big B sub big T. And so let's say I want to go H equal to 2 periods out. Well, we're going to go 2 BTs up. And so then this would be my forecast trend, but then I'm going to adjust for the seasonal component. And so here I would adjust down by whatever my current seasonal effect is. Here I guess I'm back on the line if I think my second seasonal effect is back on the line. Okay, so it looks a lot like the regression equation. I just go up however many slopes I need, but then adjust the seasonal part. That's the additive model. Now, the multiplicative model multiplies by some seasonal adjustment factor. So this would assume that my predicted values go up by a multiplicative constant. For example, maybe in second quarter my sales are 10% higher than the trend. Okay, so my seasonal effect for second quarter would be 1.1, and maybe they go down in the third quarter by 10%, which would mean the seasonal effect would be multiplying by 0.9. So let's say that my forecasted line value is 100. Well, an increase of 10% on 100 would bring me up to 110, whereas a decrease of 10% would bring me down to 90. But if my line were at, say, 500, then an increase of 10% would be an increase of 50, and a decrease of 10% would be a decrease of 50. So that's what this multiplicative model allows for. Remember that the multiplicative model often looks something like this, where the seasonal effects start out small, but then as my Y values increase, the seasonal values get exaggerated. And they get exaggerated as I go further out. And that's like the 10 versus 50 thing that I was just talking about. So it's like the seasonal effects fan out as my Y gets bigger. We can also allow for dampening. So remember what dampening is all about. Dampening is where we want to be more conservative the further out we go. And so we capture this with a geometric series. So instead of my forecasts into the future just following a straight line, they're going to start following almost a straight line, and then they're going to flatten out and approach a limit that we discussed in my video on Holt's method. So this would be the damped forecasts. So that's how we're going to make our predictions. We just add some sort of seasonal adjustment, either an additive one or a multiplicative one, and perhaps we also want to take care of our damped trend, almost exactly like what we had with Holt's method. Well, how do we handle the smoothing part? Well, the smoothing is going to be very similar to simple exponential smoothing and Holt's method. So as a quick review, the update equation for simple exponential smoothing looks something like this. Y sub t was just alpha times my current value of y, and then I give weight 1 minus alpha to my previous level. So L t minus 1, which would be my forecast of what's going to happen at time period t. So we give weight alpha to the new information, 1 minus alpha to the previous information is the way I like to think about this. So if you have a quickly changing series, you'd want to give a lot of weight to the new information and not much weight to the old information. Alternatively, if the level's not changing much, then you don't want to give too much weight to this. You want to give more weight to the older information. You want to be able to use more of that old information and not just pay attention to the latest, what's happened most recently. Okay, with Holt-Winters method, we're basically doing that after deseasonalizing the data. So I'm going to subtract off the seasonal effect from the new y. So that's like I've just deseasonalized my data. And we give that weight alpha. We give the previous estimate of where I thought my level was going to be at time period t. So that's where I was before plus the slope. I give that 1 minus alpha. The slope smoothing equation is exactly what we had from Holt's method. So what's my current change in level? Give that weight beta. So beta is my hyperparameter, just like alpha is. And then my previous changes get weight 1 minus beta. With Holt-Winters, we're going to add a new smoothing equation and parameter, gamma. So gamma controls the smoothing for the seasonal part of this. So in order to get at the seasonal part, I want to detrend what just happened. So here's what just happened. I'm going to get rid of the trend part, which leaves me with just what is the seasonal part. So the way to think about this is, with additive data, my observed data is, my observed data is just where I'm at plus the slope plus the seasonal effect. So if I get rid of the where I'm at, the level and the trend, I'm just left with the seasonal part. So think of this as the current seasonal effect, and that gets weight gamma, and then 1 minus gamma is the amount of weight that I give to all the seasonal effects for this period up until now. So we now have an additional smoothing parameter, gamma, and we have an additional set of starting values that we have to estimate. We usually make an adjustment on these seasonal effects so that they add to 0. Just like in my little regression example where second quarter I add 0.5, fourth quarter I subtract 0.5, the other quarters I add 0, and so the average value is 0. For the multiplicative method, the updates are very similar, except that since my seasonal effect is multiplicative, instead of subtracting the seasonal effect, we're going to divide by the seasonal effect to deseasonalize the data. So just take the y value, divide by the seasonal effect, and that's going to give me the this trend part, the level part. And likewise with the seasonal effect, instead of subtracting off the trend part, we're going to divide by it, because with multiplicative data, remember, my YT is the seasonal part times the level part, times, this was the updating equation. So the level plus my trend. And so that's why I'm dividing by the level plus the trend times the seasonal effect. So S times this is equal to Y is the way I like to think of it. Just as we adjusted the seasonal effects so they would sum to 0 for the additive effects, for the multiplicative model, we adjust them so that they sum to M. So if I have quarterly data, on average, the seasonal effects equal 1. We want the, 1 times something doesn't change it. So that's why we want this, the seasonal adjustment effect to average 1. Well, let's now go do some examples. I'm going to start with the retail data set, which we did a while back. I think we did this in the back when we covered the decompositions. This data set gives us retail employment by month. And so here's our data set. You can see it goes back about 5 years, and we've got data for every month. If we do an auto plot, this is what we see. I see a very strong seasonal pattern. So there's a spike. This is a spike every December. Then Christmas is over, and a lot of retail workers get laid off. So that's January and February. But then things build up again throughout the year. So a very strong seasonal effect. The other thing that I see is a trend. So it looks like things are getting better. And then what happens is the financial crisis hits in 2008, and retail employment drops a lot. Okay, so this is the December value for 2008 compared to where it was before. But then what we see is that things actually start getting better again. And this is a recovery. It takes a couple of years to get back to where we were, but after that drop, things get up, get better again. So this is telling me we need to have a fairly flexible model to capture the fact that there was that big drop, and then the trend part is going to reset itself and start increasing again. Well, I'm going to go look at the box Cox value. I don't trust it, so I'm not going to do any transformations on this. I don't think we need a quadratic transformation, which is what that's suggesting. To fit a Holt-Winters model in R, there's a couple ways. If you're using the forecasting library, as I am, we can use the HW function. There's actually another function, Holt-Winters, capital H-O-L-T, capital W-I-N-T-E-R-S, that's part of base R. But let's just use the Holt-Winters function. When we look at the help page, it's just like all the other forecasting methods that we have. We give it data. We tell it how many periods we want to forecast into the future. With the Holt-Winters method, we have to tell it whether we want the seasonal effects to be additive or multiplicative. And that corresponds exactly to whether I have this additive seasonal effect or the multiplicative one. The damped argument indicates whether or not to use damped trends when I forecast into the future. Level gives me my prediction intervals that are going to be forecast out. Then we have alpha, beta, and gamma values, which I can specify if I want to give it the smoothing parameters. If I don't give them those, R just estimates them automatically. Phi is the dampening parameter. Lambda is whether we do our Box-Cox transformation, and then bias adjustment tells whether or not to give the median or the mean when we make forecasts. Okay, so let's go fit this one. the only thing I really need to tell my model is I want an additive one. Actually, it would have done that anyway. Additive is the default. And let's go take a look at what we get. So what we see is that the original data is shown in black, and then here's the future forecasts. And so we've, I think, done a pretty good job of capturing the seasonal effect. So it looks like every December is going to be great into the future. Moreover, we've captured the trend. So after the financial crisis hit, we see a new trend where things are getting better after that sharp drop. And so Holt-Winters has adjusted very nicely to capture that. One thing to note is that the prediction intervals are pretty wide around this. And I think the reason for this is we had to reset after the financial crisis. So we couldn't rely on our trend and our level from the beginning of our data set. We had to really pay attention only to the last part of our data set. And that's why the prediction intervals get so wide. Let's now take a look at the model estimates themselves. You can see those in the fit dollar model component of the returned list. What we see is that HW has used cross-validation to estimate the three smoothing parameters. So alpha is 0.56, and what that says is that we're going to give 56% of the weight to the current observation. The remaining 43%, 44% of the weight is given to the previous observation. So what that's saying is we're given a lot of weight, what's happened most recently. I think the reason why we're giving so much weight is because we did have that financial crisis. We need to really pay attention to what's happening recently. The beta parameter is the smoothing parameter for the slope. So the value of, call it 19%, says we're going to give 19% of the weight to the current slope estimate and 81% of the weight to previous slope estimates. So the slope doesn't rely as much on the current slope as the level did. The level put far more weight on the current level. But that trend does show up in our forecasts over here because we clearly see an increasing trend. When I look at the gamma for the seasonal parameter, the estimate is very small. And what that's really telling me is we're going to give roughly equal weight to all of our seasonal effects. So it's not like we're going to give more weight to the most recent one. What we see down below are the estimates of the initial state. So remember, we have to estimate the initial level, the initial slope, and the initial seasonal adjustment factors, and here they are. To be honest with you, I don't use those initial level estimates much at all. Let's go back to the course packet for a minute, and I'd like to walk you through another example. You've got my code here, but there's a lot of output associated with it, so I think it's better to do this live. So we're going to head back to R. We're going to fit a model for the Amazon data. However, I'm going to use a test and training set, and we'll use the test set to do some model selection on this. What I will do is use the data through first quarter 2015 as my training set. The remaining data will be my test set. Let's start with an additive seasonal effect, and we're going to forecast out 20 periods into the future, and I'll only use my training set to do this. Let's go look at our auto plot, and the way I've set this up, the red line is showing the original observed data, and then the blue line is going to be the fitted data. What we notice in the scatter plot is the fit is not very good. So what's happening here is there's really exponential growth, but the basic Holt-Winters model is not accounting for that exponential growth. So what we see is basically a continuation of this trend that we saw in the most recent couple years, linearly out into the future, as opposed to exponentially out in the future. This Holt-Winters additive model is not very good. I want to point out one more thing about our fits. I want you to observe the seasonal effects in this plot. So the amplitude of the seasonal effect roughly matches what we had in the most recent year or two. It's not getting wider as the level increases. Those are two big problems that we have with this model on the Amazon data. Well, let's fix the second one of those problems by changing the seasonal effect to being multiplicative. Let's go look at it. And what we see is now we can observe that the estimated amplitude of these effects increases with the mean. Okay, so that's very much due to the fact that we're using a multiplicative seasonal effect instead of the additive seasonal effect. So if that's not clear, let's go back to the course packet for a second, and it should be clear once we look at the multiplicative model. So when we go back and look at the way these models work, you'll see that we're multiplying by the seasonal effect, we're not adding by it. And so if the seasonal effect is, say, increased by 20% in December, an increase of 20% in December means a lot more when this trend plus level part is high than when it is low. That's why the multiplicative seasonal effect allows for the amplitude to increase over time. The fit is still very poor because we've missed the exponential growth. So the way we're going to address that second problem is to use a Box-Cox transformation. I don't really know what transformation to use, so we'll just let the HW function choose it using the Box-Cox lambda function. Again, we'll project out 20 periods into the future. I'm going to do some bias adjustment when we create our fitted values. Well, let's go look at the plot. What we see is much improved. We're clearly getting the trend. The seasonal effect is increasing. Let's go look at the model parameter estimates. R has selected the Box-Cox parameter be 0.083, which is mighty close to 0. Remember that a Box-Cox transformation of 0 means take the log. We're almost taking the log. Our author and I recommended simple values of Box-Cox, so I would just assume round this to 0. So let's go try this again with a lambda of 0. Now, one more thing to notice, both in this model and the previous model, I'm doing an additive model because I'm taking this Box-Cox transformation. So when I log the data, that stabilizes the variance for me. And so I don't need the multiplicative seasonal effects. I can just use an additive. I can't tell the difference between this plot and the previous one. Maybe there's a slight difference. It looks like here the blue line underestimates things with the log. Maybe it's gotten a little bit better, but I would say both models are very good. Now we can go look at our parameter estimates. I think we're getting close to a pretty good model here. What's interesting on this is the alpha is substantially decreased from what we saw with the retail example. We're not giving that much weight to the current observation. The slope is pretty much constant over time because we don't really need to give more weight to more recent observations. But the seasonal effects, we give quite a bit more weight to the most recent seasonal effect in this model. Well, I want to try one more model, and that is with a damped trend. Remember that damped trends get more conservative the further out we go. So the trend component of this is going to flatten out and approach an asymptote as opposed to continuing to go up in a linear way. And what we see is the damped trend does not look very good. So I'm not very pleased with this. These are the types of things that you go through when you build a model. When you come into something, you don't know exactly what's going to work, so you have to do exactly what I've been doing. We could go look at the parameter estimates. since this is such a bad model, I'm not going to really try to interpret. Well, another thing that we can do is apply this to the test set. So we can do this with the accuracy function. And so this was the first, let's go back to the first model. This was the one with the additive seasonal effect. We have it for both the test and the training set, all of our fit measures. If I look at the multiplicative model, you'll see it, it actually gets a little bit worse. So RMSE goes from 20.7 to 21.6. Mean absolute error gets worse. Mean percent error gets worse. MAPE gets worse. So Model 2's pretty bad, as we already suspected. When I use the box Cox, things get much, much better. So RMSE goes from around 20-ish down to about 6.5. Mean absolute error likewise is cut by more than a third. So we really like the box Cox transformation. If we use the log, what I see is that things get a little bit better. The root mean squared error is slightly better. Mean absolute error actually gets quite a bit better. So I would definitely prefer the log model. What we do see is a bias kind of in the other direction. So the mean error is positive using the box Cox. It's slightly negative for the log. And that was what I was referring to in the plot, where it looked like one was overshooting it, the other one was undershooting it. And so I'm going to make another plot in a second where this becomes even clearer. If we were to compare this with Fit 5, that's the one with the damp trend, that one really is not very good, as the plot was also showing us. So the final thing that I want to do in this example is to make myself a plot that will compare all of these models at once. And so you've got my code here, and we'll plot the original data. That'll show up in black, and then we'll get the fitted values as well as the predicted values. And what we see, turning off our prediction intervals, is basically what we saw before. There are two models that are competitive, so the box Cox and the log model. And what we're seeing is that the log model is slightly overestimating what's happening, while the box Cox is slightly underestimating what's happening. But both of these are doing a pretty good job. Perhaps the seasonal swings are a bit large, but other than that, we see the errors are quite good. All three other models are really not worth considering for this. That's it for my lecture on the Holt-Winters model. We will see how we can generalize all of these models in my next video.